All right, so this mini lecture is going to look at the idea of thermal equilibrium. Now, this is not a new concept for you. You in Physics 1 or in previous videos, if you were kind of going through our little whole series of Hopped Up on Physics, you learned about the conservation principles in mechanical energy, right? That the total energy doesn't change. The total energy remains the same. And thermal equilibrium is that same sort of idea, and we're going to look at it in terms of the energy in thermal energy. So you were first introduced to the idea of a system back when we talked about mechanical energy and momentum. So there were two types of systems, remember. The first was an open system. And an open system, as we are now going to use it, is that energy and mass can leave the system, come and go. Okay, so energy and mass can leave the system. So this is kind of like our human body is an open system, right? We take in food, we release waste, we breathe in gases, and we expel gases, right? So we kind of have an open system. Energy is released, heat goes off of our body, and things are taken in, more mass, and mass leaves the system. So that's an example of an open system. What we're going to actually focus more on and analyze is what we call a closed system. And these are the type you've heard about before in our previous studies. And this means that energy is not lost. Mass is not lost. Mass is not lost. But energy could be. Okay, and so like when you did mechanical energy, some of that energy was lost to heat, for example, or to sound, okay? However, we also can look at what we call an isolated closed system, so kind of a subset here. And in an isolated system, no mass, no energy lost. So that's what we're going to start with. An isolated system, okay? No energy is lost, no mass is lost. So we're going to focus on that, or we're going to focus on nearly isolated system. It's a good model for most of what we're going to do. So what does this mean in terms of thermal energy? Well, it means if I have two elements in my system, two parts of my system, and they start out at different temperatures, then energy needs to transfer between them until equilibrium is reached. That's the conservation of energy principle. And so if we have two objects at two different temperatures, then thermal energy is transferred from one to the other, high temperature to low temperature, until thermal equilibrium is reached when the two temperatures are the same. This happens so that net energy transfer is zero. So we get this transfer of heat energy until the net transfer becomes zero, where the temperature now is the same, okay? And if two objects are in thermal equilibrium with a third object, then all of them are in thermal equilibrium. So this can extend to more than just two objects that I started out with. That's what we call the zeroth law of thermodynamics. It's pretty obvious, but it's actually an important thing for us to recognize that basically, if something is within a system, all things are going to equilibrate from a temperature standpoint, a thermal energy and temperature standpoint, okay? So, if we put that kind of into equation form, what does this thermal equilibrium mean? Within a system, again, it means that the heat the heat that's lost from one object in the system has to equal the heat gained by the other object in the system. Pretty straightforward. It means that the energy out, we can talk about it in different ways, of one object in one thing in that system has to equal the energy in to the other thing in that system. And I'm just going to simplify it with like the two object idea. Okay, so the energy out has to equal the energy in. Again, this can be across multiple things if necessary. And then the last way we can kind of think about is that the total energy, total heat, if I add them all up, we have no change. Okay, so the sum of all the heat when we have transfer is equal to 0. The sum of the heat transfer, so the heat is the transfer, remember, is equal to 0. All right, so what one object gets, the other one loses. The heat from one goes to the other. Okay, the energy from one goes to the other. The heat change in one is the same as the heat change in the other, so that there's no net change in heat for the system. Okay, so this is no different than our conservation of energy principles before. It's just now in terms of heat. So let's just do an example and we'll see how this works, and I think you'll feel really comfortable with it. So let's pull up that example. Let's imagine you pour a hot cup of coffee into a glass cup or a glass mug. Okay, a hot cup of coffee in a glass mug. And the coffee is at 90 degrees. 90 degrees? I forgot what I put. 85 degrees? What did I put? 90 degrees. And the cup is at 20 degrees. So it's sitting kind of in standard room temperature at 20 degrees. I just pull that coffee. It's not boiling, obviously. It's just at 90 degrees, and it's mostly water. We're just going to approximate it as water. And I pour it into my cup. Once the thermal equilibrium is reached, what's the new temperature? What's the temperature of the coffee in my cup? Is it going to stay 90? Let's check it out. All right. So what do we got here? We know that the total energy, the total heat transfer has to be 0. Okay, the total heat transfer has to be 0. So the heat that the coffee, in our case, loses, right? Plus the heat that the cup gains has to be 0. Now, we know that heat goes from the hotter temperature is going to lose that heat. The lower temperature is going to gain that heat, right? Because we need to find an equilibrium, something in between. So the heat from our coffee, well, that's the mass of the coffee times the specific heat of the coffee, which we're going to model as water, times the change in temperature. So the final temperature, what they equilibrate to, minus what it started at, which was 90 degrees. Okay? That plus our mass of the cup times the specific heat of the cup times its change in temperature, whatever that temperature is, because they're going to get to thermal equilibrium, minus 20 degrees. We know that has to equal 0. Okay? So what does Q come from? Remember, that's our relationship, that the heat is equal to the mass times the specific heat times the change in temperature. Okay, so that's where our Q comes from. So when we solve for this, what happens? Well, the mass of the coffee, we're told, is 0.3 kilograms. Oh, I don't need units. Now I'll put those in there so we don't get ourselves confused. We said we're going to model it as water, so the specific heat of water is 1486 joules per kilogram times temperature. T minus 90 degrees. Plus the mass of our cup, we're told, is 0.2 kilograms. The specific heat of the cup, well, we're dealing with glass, and you can look up specific heat values in a table. These are standard values. Of glass, it's 840 joules per kilogram degree Celsius. And its temperature change, whatever T is, minus 20. All right, so all I got to do now is solve for T. Okay, so this is pretty straightforward algebra, right? That we can solve for T. And we find that our T, our equilibrium temperature, ends up being 86 degrees Celsius. So solving for T, we get 86 degrees Celsius. All right, which means the cup is at 86 degrees Celsius and the coffee inside of it, I was going to say tea because I'm thinking about temperature tea. The coffee inside of it has cooled to 86. The cup has warmed to 86. All right, so just using this idea of thermal equilibrium, using our specific heat relationship to solve some problems. All right, good job.